Hello and welcome to the 6th lecture in the series of Knowledge Miles webinars, part of the Lord Mayor's lectures on behalf of Professor Michael Manelli, whose theme for his mayoral year is Connect to Prosper. In this series of online lectures, we address the connections in and around the square mile of the City of London, connections which can and are helping us to tackle the challenges facing the world today. I'm Dr. Kevin Parker, Director of KKR Associates and Science Advisor to ZN Group in the City of London. I'll be chairing this session and taking questions and answers afterwards. Our plan for today, this introduction from myself, our keynote lecture from Dr. Tom Davis, and then approximately 20 minutes of questions and answers. We're very pleased that Tom is able to join us today. He's the co-founder and the Chief Technology Officer of Oxford Signa, a fusion technology company that aims to provide materials technology and solutions for commercial fusion energy. And I even understand what some of those words mean. He holds multiple patents and has published more than 10 fusion-related scientific papers. He's got a PhD in material science from the University of Oxford and is a liveryman at the worshipful company of science instrument makers in the City of London. Thank you, and over to Tom.
Thank you for that introduction. I'm just going to share my screen. If I get it right. Can you see my slides? Or can you see?
Yes, we can see your slides. Yeah.
Sorry, it doesn't turn on this side. Okay, so thank you for the introduction and thank you for inviting me to speak here today at this Lord Mayor's lectures on Knowledge Miles. As mentioned, I'm Tom Davis. I co-founded this organization called Oxford Sigma, but majority of this talk would actually just mainly focus on fusion energy, not so much on the technical aspects, though I will cover some of that, but more surrounding what's happened in the sort of the last 5 years, from sort of public perception, but also regulatory aspects around the world and recent funding announcement, recent private fusion enterprises, venture capital. So give you a bit of a state of play of what's really going on, and whether we can actually get to where people think fusion should go, and that's obviously power production of some sort in the coming time. So that's kind of the intent of the talk, and it gives you a bit of that vibe aspect. So as mentioned very kindly from Kevin, co-founded this organization just over nearly 5 years ago now, whilst I was finishing my PhD at Oxford University in material science, focusing on fusion materials. And now we've grown an organization where we work with quite a lot of fusion players in the world. So this comes from, I try to give as the latest news as best I can over the last couple of weeks as well. There's some more positive news coming out. So this is kind of the idea behind the talk as well. So thank you. So we'll start off with essentially what's the point of this, of fusion. I mean, looking out on the screen, you've got a picture of that. This is our sun, obviously in the solar system. This is conducting fusion and reactions all the time with hydrogen and hydrogen fusing together. It can do that by the one confinement method. How you confine that reaction is generally by, in this case, gravity. So the sheer mass of the sun is what maintains the reaction. So also another reason is it's extremely difficult to do is the actual hydrogen you fuse two atoms together. It's such a difficult reaction to do on Earth. The sun can achieve it by its own gravitational pull, but it's also a very weak reaction, which is a positive for humans because it ends up defining the lifetime of the sun. In this case, obviously, it's billions of years long, and that's one of the major factors for that is actually the fusion reaction rate for hydrogen is so small. It contains, you need this size of a mass to actually can do it. So we'll talk about it in a minute, but there's a different fuel cycle on Earth we're looking at. But the aim of the game is to obviously harness the sun sort of physics reactions on planet Earth. We can't do that by gravitational confinement. Obviously, it just wouldn't happen. So there's other methods that we produce in doing this. There's three main methods which I'll go on, but one is levitating with magnetic fields. The other one is confining it for its own inertia, so the implosion of fusion fuel, and then obviously that would extract that release energy from the fusion reaction itself. And the aim of the game is generally to obviously make more energy out than you put into the fusion fuel. That's a, you know, it's a zero sum game otherwise. And that's what we've been chasing since the beginning. You know, since fusion became declassified in the 1950s and 60s, we've always been chasing this. Can you make more energy out than you put into the reaction? And so I'll start off with this whole talk and saying that's actually been achieved. As of December last year, it was announced in the news. I'm sure some of you probably saw it in the news on BBC front homepage. But there's a facility in the United States called National Ignition Facility, NIF. It's hosted by Lawrence Livermore National Lab in California, and it's a laser fusion approach. So I mentioned inertia, so able to implode fuel by its own inertia, and the inertia is provided by X-rays, and those X-rays are provided by, you see on the right here on your screen. There's like a hologram, like a gold hologram. This is a 3D rendering, but the idea is that you shine lasers inside it on all sides, and generates X-rays. Those X-rays are directed towards the fuel in the center, which is a frozen fuel of isotopes of hydrogen. But the idea behind that is that it actually compresses the fuel to the point where it fuses. And as of last year, we've now demonstrated that you can create more energy out than in. It's always been obviously chased, but now it's been built for reality. So one of the two equations in this talk at the bottom is Q scientific, and Q is like the value that everyone chases. You've got to have Q greater than 1, which is the ratio of the fuel of the raw energy released by, in this case, DT fusion, which is, I'll talk about in a minute, deuterium and tritium, divided by the energy you input it from the laser. This is defined as just the energy gone into the laser, into the fuel itself, rather than the engineering mindset of people with how much energy was taken from the national grid or things like that. That's Q engineering sort of perspective. That's what we're trying to chase over the next decade. But from a scientific standpoint, we have achieved ignition. Another really important point about this was done in December last year, but since then this has been achieved twice now. Again, in summertime in 2023, and it's been announced. That gives us confidence in the industry that we're able to achieve this multiple times, and we've been able to fine-tune the parameters at least in inertial confinement fusion, which is this laser fusion approach. So it's given us quite high level degree of confidence now that it can be done. Now the question becomes, can you harness it in a useful manner to generate what people want in the world generally is electricity or heat production or some sort of useful source of energy on the outcome. So I just wanted to start that off. That's I would say probably one of the biggest announcements in a very long time in fusion, and we would expect more to come. So to fuel types, this is a somewhat important note to make, and why things are done. So the sun I mentioned was hydrogen, just natural hydrogen you can find anywhere. That's not suitable on Earth or any other planet in the solar system generally, because the reaction rate is just way too small. The highest reaction rate, another way of saying it is just the probability of reactions the highest, is between two isotopes of hydrogen. One's deuterium, which is found in seawater, and the supply of that is, to all intents and purposes, we don't have to worry about that. And then there's also tritium, which is the second isotope of hydrogen, which has got 2 neutrons near. So you can see them two sort of green balls on the screen that signifies neutrons. Putting them together, generally on the right curve is the most important curve really to think about when you think about fuel choices, and this defines basically the way you do fusion from here onwards out. We've been chasing the green curve, the majority. There are exceptions. There are organizations out there looking at deuterium helium-3, for example, and proton boron is another one. But the green curve is generally the one we follow, and that's because you need the highest reaction rate on the y-axis here, so the highest on the curve, with the lowest temperature possible. And just to give you a bit of an idea on temperatures needed to fuse, I mean, if you take 10 kiloelectron volts here on the y-axis, the conversion of that to degrees Kelvin, this is 116 million degrees Kelvin, centigrade Kelvin, Fahrenheit, it's all the same by that point. So you can get the idea of the sort of temperatures. You're talking 100 million degrees. There is some quantum mechanical effects you can take advantage of, so it's a bit less than that, but you're still talking 50 to 100 million degrees to enable DT or tritium fusion, which is the fuel type you saw in that laser fusion implosion. So that's what we're demonstrating. That's what we're chasing. Just going forward. Now I mentioned how to fuse things. This is essentially 3 major ways to fuse things. There's always exceptions, but generally the put into camps. We've got magnetic confinement fusion, which is probably the most mature in technology. I kind of alluded to it, but instead of having gravity confine your plasma or your fusion reaction, you confine it by large, strong magnetic fields. Here, generally, you can see this like blue shape, which is a D shape. That's a magnet, generally superconducting of nature, and then you've got a central column in the middle. And then it forms a donut, a plasma donut. And the idea is to have that plasma, which is confined in a way that can't, minimize the touching on the walls. It's, as we'll probably allude to in the future, and what my organization does is, what is the first raw material going to face such a 150 million degree plasma? There are some options out there. And it's behind, making sure that magnetic field is able to confine the plasma. So that's one of the majority, which is the most sort of researched and built reactors around the world. And also they're also named sometimes on an acronym tokamak. So you might have heard that as well, but that's a method of magnetic confinement fusion. There's also inertial confinement fusion. So this is the one which I mentioned about NIF. This one has achieved Q greater than 1, and it's essentially lasers into a pellet in the middle and it compresses it. And there's also a mixture in between, which is kind of a hybrid, and it ranges significantly in designs. This is just one of the many, many options. The idea is you, instead of firing a pellet of fuel, you fire sort of a plasma, which is a deuterium-tritium plasma, and then you compress it in some sort of method. Compression could be with another plasma. You can compress it with liquid metal. The idea is you want to combine this compression. And what all these 3 fusion approaches are doing, and what everyone is trying to achieve in any reactor design going forward, is essentially the equation at the bottom. So this is the second and the last of all the equations I've got. And it's called a triple product, also called the Lawson criteria, named after John Lawson from UKAEA 1955, who came up with this equation. And it's essentially, there's a value, there's a number. In this case, this is for deuterium tritium. It's a threshold value. So you need to be above that threshold value for your fusion reaction to what we call ignite, which is burn, where the energy released by the fusion self-heats itself. So it maintains another fusion reaction by its own heat, and vice versa, burn reaction. So it's a triple product. So there's 3 things you've got to consider: plasma density, which is N, T is temperature, and then confinement time, how long you confine it for. Now, if I went through all 3 different options, so if you take magnetic confinement, the number density for plasma is medium, I would say. The temperature is again medium, and then also the confinement time is long. So you want these to confine for, we're talking hours, days, years. That's the sort of approach you would become a reality for power stations. On the far right is the somewhat opposite. So, for example, under the implosion conditions, the plasma density and temperature is significantly high, but the confinement time is significantly low. So we're talking nanoseconds of time to confine that. So there's we're still trying to achieve that numerical value. And then magneto-inertial confinement fusion, which is in the middle, is a mixture. Depending on the approach, it's a mixture. That's most of the technical, by the way, for this whole talk. So I'm very sorry if you were expecting more. The rest of it is technical in the mains of government perspective and or regulatory aspects and law. So I mentioned this is a latest update from the Fusion Industry Association report, came out in summer. So this gives you the number of private fusion organizations which have received private equity of some sort, pursuing a mission to generate electricity or some sort of useful energy output from fusion reactors. And you can just see around the world, this is as of summer 2023. There has been a new one since then. But you can tell very quickly, USA has the highest concentration of 25 companies. It's 1 in Canada, 3 in the United Kingdom, 3 in Germany. If you asked me this question 2 years ago, there was basically none in Germany. Now there's 3. And Sweden's fairly new. China have 2, Japan have 3, Australia has 1, and New Zealand was founded, I think, this year. So they're also founded as well. So you can sort of see there's a high concentration in the United States. So now we're going to jump to what public fusion are doing, and then kind of whistle on to what regulatory stuff aspect is. So this is public, government supporting, developing fusion. So the roadmap is pretty much at very high level, but there's been test facilities over the last, numbers of decades. The one I'm going to talk about is Joint European Tourist Jet, which is in the UK, as well as the largest tokamak. It's been very successful. It is shutting down very soon. It was built in 1984, multiple upgrades. It's been a world leader in developing tokamaks as a power source for the future. The successor to that is called ITER, which is an international program built by over 35 countries are funding this. This is fast plasma. 2025 is going to be delayed probably over the coming years. I'll show you some construction photos of it. This is meant to produce 10 times more energy out than in when it produces, based on, again, on tokamak. As you can see here, this is that donut shape in the middle of the plasma, and then the yellow section is the magnetic fields, the toroidal coils, and then you can see various subcomponents in there as well. So that's a technology integrator demonstration, and that kind of really integrates the last sort of 40 years of effort from 2000 prior of all the technologies and bringing them all in one device. That's the first time it's ever happened, and I'll show the latest updates on where that is. And then publicly post that, the idea is that your transition towards this energy demonstration plant, 2040s beyond. The EU has a program, South Korea has a program, United Kingdom has a program I'll talk about, India has a program, Japan has a program, and recently the United States have one, but slightly different. It's not a public one, it's more of a public-private approach. Mentioned construction. This is ITER, March 2009, South France, Cadarache. You can see on the map here, Cadarache is down here in lovely South France. And you can see the land was flattened for ITER, but fast forward just under 10 years, you can see there's quite a large activity on this site now. So the only things I'll really point towards is that 3D CAD model you saw. It's going to sit on top of this tokamak pit here, this concrete pit, and there's a lot of auxiliary buildings around it. But that's 2018. This is now actually May 2022. So as you can see, one of the first segments of what we call a vacuum vessel, but this is one of the many vacuum vessels which will come together and sit around that central column post. You can see the support structure there. So we're, the world's putting this together slowly over time. And this is from March 2023, and now the site's a bit different, a bit more built up. So the tokamak sits in this middle bit, this mirror building here, and then there's assembly hall just to the left of it, and these are various assembly halls, magnet winding halls around here. You obviously got the electrical distribution on the rear there, the pit of the photo, and then various auxiliary systems. There's the tritium handling system just around here as well. This is fully, this is as you can see, a large scale project. It's about circa between $20–25 billion. The number's not officially been released, but it's around that sort of value. This is again driven by the public institution of ITER. It's an ITER organization, and it's funded by 35 countries around the world. So this is the latest activity going on right now. In parallel to all this, the UK announced in late 2019, post sort of Brexit, Boris Johnson got it, was just into power. The UK Atomic Energy Authority, which is the UK's national lab on fusion, has their main campus in Oxfordshire, where we're based. Announced a thing called STEP, which is spherical tokamak energy production, and the idea behind this is that it's an ambitious program to deliver a prototype fusion energy plant targeting 2040 and a path to demonstrate a path towards commercial viability. STEP will not be a commercial entity; it'll be a demonstrated prototype device, and it's led by UK Atomic Energy Authority. And there's been some very recent news. This was in 2023 this year in Telegraph about the UK is about to launch. I'll talk about what that really means in there. Launch what we call, at least they were coining it as a polar mission of nuclear fusion in 2024. And the idea behind that is this STEP program will build, a tokamak device for, and it will produce electricity. Just not in a commercial sense. It will just, it's more of a demonstration piece by the government. And again, this is managed, financed by the UK Atomic Energy Authority, which is obviously a non-departmental body of Department of Energy, Energy Security and Net Zero. So moving on, this is now February of this year. So that was 2019. Now this is February 2023 this year. So the government announced a major step in STEP, which is, excuse the pun. So they take a step in, they formed a company called UK Industrial Fusion Solutions Limited, which will be solely owned by the UK Atomic Energy Authority, which has the mission to deliver STEP as a power plant production prototype device by 2040. So there's been a new body formed, But moving on a bit further than that, now we're in the land of this end of this year, coming next year, 2024. The STEP program is undergoing procurement of an engineering partner and a construction partner and a fusion partner. So these are three major partners for the UK that companies spun out from UKAEA to actually, construct such a fusion reactor for the future. So these contracts are underway. The competition is going to start next year, and then by the end of sort of early 2025, we should find out who is going to be the engineering partner in the country and who's going to be the construction partner. And just to give you a bit of an idea, as you can see on the right here, STEP has a site already located, and it's been located at a place called West Burton, which is an old coal-fired power station, and you can just see in the distance here, which is up in West Burton, Nottinghamshire, just on the border to the north. And then STEP will be sat on this coal ash field, essentially. So STEP is going to be built in that, and there's a River Trent going around. So the site's already been located. The company to deliver it's been founded, and now the UK government is procuring the two large construction partners and engineering partners to deliver such a machine by 2040. So as you can kind of see, there's been quite a lot of activity in the UK as we speak. Next sort of bit is very recently, again, we're talking October, November this year, just gone. The UK announced an update to its policy on fusion, which is one of the few countries in the world to have a policy dedicated to fusion energy. I would highly recommend reading it if anyone's interested. It really sets out the tone, the agenda of kind of what the UK are going for in this sense. It really outlines in there, it's another extra funding round for £650 million package for fusion, announced by the nuclear minister Andrew Bowie at the IEA Fusion Conference, which was held in London in October. But it's a really quite comprehensive package, which covers not just technical, but it covers how the skills pipeline looks, how technology transfer looks, sort of supporting small businesses, and then also supporting sort of infrastructure projects which can enable fusion. So they're really thinking quite laterally when it comes to the strategy. And also very lately, you might see in the news next week, there will be, it's kind of US, but it's all kind of related. The United States will announce a policy or some sort of update on their nuclear fusion strategy at COP28 by John Kerry. So I highly recommend if anyone's interested to hear what he says about what's coming up. So it's a pretty exciting news for fusion itself. So moving on to regulatory bit, this is a bit, some people might like this, some people might find it boring, depending on if you like regulation. But prior to October 2021, there was really no sort of official stance on where fusion energy comes under regulation in the UK. As of October 2021, that has now been made. There was on the left, there's a document on the government website you can download, which basically outlines the method on regulation. Then you also got some middle document in the middle screen was a consultation period, and then some answers to the consultation period. And essentially, fusion kind of says here. So there was an act of parliament which has now been given royal assent as of last month or early this month, sorry, called the Energy Act 2023. But in the Energy Act had a section on fusion, and what it states, it pretty much says, I'll read it out because it kind of explains very nicely where fusion sits. So there's a thing called Nuclear Installations Act 1965, which defines basically nuclear regulation and who and what site constituents a nuclear site, and then that's to be regulated by the Office for Nuclear Regulation. There's an exception now in subsection 2A, which has now been put in, it's called fusion energy facility, which means essentially anything purpose of installing or operating a plant designed or adapted for the production of electrical energy or heat by fusion, and or doesn't have any sort of nuclear reactor inside it, is it basically exempt from this. So in other words, it comes under the Health and Safety Executive from a safety regulation, and also the Environmental Agency for an environmental base. The reason why that's important to make note is because it gives a bit of certainty in the approach to fusion, but also certainty in investment in private, and so you can see that pathway going forward. Now, flipping over to the United States, the only three things really major has happened in the United States, which is worth mentioning, is there was a law passed in 2018 called Nuclear Energy Innovation and Modernization Act. The only real thing in there which is important for fusion is that it actually clarifies that advanced fission and fusion will be regulated by the Nuclear Regulatory Commission. And then it gave an instruction to the US nuclear regulator to have a framework in place for analysing and allowing the licensing of advanced fission and also fusion. So the next slide will talk about the outcome of that. And also the White House in March 2022 announced a very bold statement from the Secretary of State for Energy by the Biden administration, titled "Developing a Bold Decadal Vision for Commercial Fusion Energy." And in a nutshell, the idea behind that is the US government wants to see private fusion be successful within the decade on a commercial basis. So it's a very strong message to the industry. And I'll talk about what came out of that in a minute. Last point of regulation, the United States has now voted on how they're going to regulate fusion. They knew it's going to be regulated by the Nuclear Regulatory Commission, but the question was how it's going to be regulated. And there's an option paper, which again, people can read that later, but essentially puts forward a technology neutral basis for licensing and oversight for fusion. And then it was all voted in come April the 18th by the Commission on the top level, and now fusion is now not under fission regulation. It's going to have its own dedicated fusion section within Part 30, which is a term in US law dedicated really to particle accelerators. So that's now again provided a bit of certainty for the fusion organizations in the United States as well. So outside those two, there's very little sort of specific fusion regulation in the world. The French have one for ITER. But other than that, right now there's been no sort of message put out. So it gives a bit of certainty in the market. Now, the last bit I'm just going to focus on is on private fusion, and then I'll wrap up there. So that's all the kind of public, the regulatory stuff. And so the UK, you can see the UK is going for a mission of building STEP. So where does private fusion fit into all this? So this is from 2021. There's a nice report from Fusion Industry Association that sums up a lot of the funding. Back then, they had about $1.7 billion of private investment into private fusion. There was some from the UK, and there was, at the time in 2020, there was 23 private fusion companies. And again, these are defined as private fusion organizations, which has the mission or the MO to produce electricity or some sort of energy production from fusion itself. This was released in August of 2021. So now there's some good updates since August 2021. A company called Commonwealth Fusion Systems, which is a spin out from MIT pursuing tokamak-based fusion, raised 1.8 billion in their Series B funding round. A company from Australia was formed called HB11. They awarded some money for their private round. Helon Energy, another private organization, spin out from based in Washington State in Seattle region, secures 2.2 billion to commercialize fusion on their design, which is a very different design, but it's worth noting. And then also General Fusion, a Canadian company, secured its Series D round, I believe it was, 130 million pound, again to do some fusion approach as well. So then every year this report's updated, but just to give you a bit of a sense, a bit of an idea of what's going on. So in 2022, it was all summed up. Now it's 4.8 billion of private investment. General approach people want to take to fusion is magnet confinement, that sort of bubble. I mentioned the magnet bubble. And there's inertial confinement, generally 8. So that's generally things like laser approaches or projectile-based fusion on inertial confinement fuel. Most people want to do electricity production in private fusion companies to give out. There's some space propulsion, some marine, some medical, but generally it's electricity generation. A bit of as an answer, when would the first fusion plant deliver electricity to the grid? This has obviously been answered by the fusion company, so of course they will choose a date which is very suitable for their timelines. So according to the private companies, 2031, 2035. Just keep an eye on that, I would say. Since that report was released, the UK company Press Up Fusion, based in Oxfordshire, spun out from Oxford University, projectile-based fusion, raises more money. Kyoto Fusioneering, spin out a fairly new company in Japan, raised more money. Zap Energy, a company based in Seattle, a different one, raised 160 million. And then, importantly, Department of Energy announces the first step in their private-public partnership for the bold decadal vision that the White House has put out. It's called the Milestone-Based Fusion Development Program. And then UK announced some cash. So now 2023, this is the latest sort of roundup. This is now August 2023, to give you a bit of an idea. Now approximately $6.2 billion has gone into private equity, into fusion, with some small bits from government investment around the world. That number's been out of date now, but it'll be updated every year. Again, people still think 2031, 2035 is more fusion. There's a bit more press. And so this is kind of where we are right now with the private organizations. As you can see, a lot of them were concentrated in the United States, some in Europe, and then some in Asia markets as well. And it's all been driven. You can see now, right, in the UK perspective, you know, you've got the regulatory aspects written down, and you can see the vision from the government, how it sees fusion playing a role in the market and in the vision going forward. United States is now organising, and they've obviously ruled on how the Nuclear Regulatory Commission is going to regulate fusion. Now the next part is the detailed part of that. That's the next sort of conversation going on. But also the United States government has released a milestone-based program, which I'll allude to in a very minute, and how that functions. So you're having all these sort of ducks lining up slowly in the row for fusion. Obviously, what needs to come with it is the technical success, which I haven't really mentioned too much here. We've obviously shown Q greater than 1 right now, but that's just a scientific break-even. It's not an engineering break-even. So over the next 5 to 10 years, that's the activities which have to occur for a lot of the fusion, especially in the private space, to overcome. A few notes of things to mention, and then I'll wrap up. A company based in the UK called Tokamak Energy, been around since 2009, spin out from the UK Atomic Energy Authority. They have their own Tokamak reactor here. There's a picture of it. They announced in March they achieved 100 million degree plasma, which is a world record for spherical Tokamak design. It's not using fusion fuel, but it's using a hydrogen and deuterium to give its equivalence, basically, about doing fusion. I mentioned Commonwealth Fusion Systems, that 1.8 billion fundraise back in 2021. They're building their reactor in Massachusetts. So this is from June 2022. You can see here, this is their Tokamak pit where the Tokamak's going to sit on. And you can see their constructions here. And in the background, you can just see there's a magnet winding building. This is as of February this year. And you can see their construction is in the background is where the fusion plant's going to sit for their spark reactor, which we can talk about in the questions. And then also, this is very recently, this is all to do with COP28 as well, but as you can see, this was taken a couple of weeks ago. But on the right is John Kerry visiting Commonwealth Fusion Systems, and that's Bob Mongard, the CEO of CFS, talking about fusion. And this is all in background to COP28 coming up next week. And then one of the two last slides is in the UK, 3 organisations have put out press statements 2021, 2023, 2022, and 2023. So that's General Fusion on the left, Canadian company, Fast Light Fusion in the middle, and then Tokamak Energy have all announced they want to build the next fusion reactor at the UKAEA campus in Culham in Oxfordshire. So that's all going ahead as they're all fundraising to construct those projects. And then also, if you're ever interested in fusion, sort of what's going on in private space for fusion, the Fusion Industry Association is very good at sort of gathering that information. So on the left here is the private fusion companies. This is a snapshot a couple of months ago. These are all the different organizations pursuing it. And on this, there's a supply chain on the right where they provide some sort of supplies to fusion as well. One last thing I'll mention, and I'll end it here, is I mentioned the US Department of Energy announces a milestone-based program for fusion. What I would describe that as is it's modeled after the SpaceX COTS program. So if anyone was following how SpaceX and Blue Origin back in the early 2000s was able to develop a company on the back of an industry which didn't exist in a commercial space, which was space industry, to supply NASA the services that it needs. The US government formulated a NASA Commercial Orbital Transportation Services called COTS, where it was based on a milestone-based program where you were promised an X amount of cash incentive from the US government if you meet this milestone technical. If you meet the milestone technical, you get reimbursed a percentage of the money you spent. And you keep doing this until you're basically technically successful in the program. So the US government has laid the foundation for fusion. This was announced this year in 2023. The awards, companies who are awarded on this milestone-based program are listed here. And they're now underway developing a pilot plant design to deliver to the US government to say we are meeting our milestones, and so they're being reimbursed. So a lot of the fiscal responsibility and liabilities left on the company, and the idea is you stimulate an industry to deliver what could be a non-commercial product today, but could be in the 2030s. So the US government are trying to form this environment for this to happen. So this has just started, and it's probably lays a foundation for private fusion to kind of become successful in the future. I'm just noting time, Kevin. It's the rest of the stuff is there's not much left, but I haven't really talked about the challenges yet or anything like that. So we can maybe lead them to the quick questions and answers if you like.
We do have some questions on that, so yes.
Yeah, I thought it would be. So I mean, in terms of this is kind of essentially the latest information that we really have on fusion from a public perspective and from a so just sort of how governments get involved and kind of where the UK stand. And you can see the UK and the US have got these sort of platforms right now, and your other, like Germany's coming up, and they've got some announcements they made on fusion this year about how they're supporting laser fusion, and you're seeing some play off between countries as well on trying to be the first person to commercialize fusion. So it's an exciting place to be in, and I'll make one point about Oxford Sigma where we sit in this whole bit. We work on materials and some of the technical challenges which I haven't even mentioned, but we work with a lot of organisations. So we're very agnostic to fusion approach. We're just here trying to support fusion and making it a reality for the next decade to come. We work on materials, the stuff we put on the walls we make it out of, that sort of box, for where the sun goes in. So that generally is where we sit in this. So happy to answer any questions from here. I'm just noting on time. I'm going to get to more Q&A of this. So thank you for listening, and happy to answer any questions.
John, thank you very much. That was great. That was fascinating. We already had a number of questions, and I will go through those, not necessarily in the order that people asked them. A fairly easy one to start with from Chris David. You mentioned the figure of $6 billion investment in 2023. Was that a cumulative figure or just the investment in this year?
That's cumulative. Good question. I don't actually remember exactly how much was made, how much was invested in 2023 alone. If I had to put a number on it, it's probably circa about $1 billion.
Okay.
If you asked the question the year prior, 2021 was the biggest number on record. It was something like 3 or 4 billion, if I remember correctly. There was a big spike just before the interest rates went up.
Good. Now I have a couple of questions about differing technologies. Charles Henderson asks, where does First Light's fusion, their projectile inertial fusion, fit into this? And we also have a question on another technology which I've just lost. Oh yes, Nicholas Bertels asks about Rolls-Royce developing small-scale nuclear energy programs. Are those things related?
I'll take the first one. So the first one is where does First Light Fusion's technology fit into like the sort of approach to fusion? You're right, it's called projectile fusion. They are the inventors of it. Projectile, the way of looking at it is you're basically compressing the fuel by its own inertia. So it comes under inertial confinement fusion. How you cause the inertia is either via lasers or via compression of some material, or in case of First Light Fusion, is projectiles. So they are projecting some sort of mass to, I think they call it an amplifier, which amplifies the shock waves, which compresses the fuel. So it's a compression via shock wave, but it fits into inertial fusion. It's another way of doing inertial fusion. And also on the second question, Rolls-Royce, I think you're alluding to the small modular reactor program from Rolls-Royce. This is a small, pressure water reactor fission. They're not connected with the fusion program on that, as far as I'm aware.
And relating to that, we have a question from Tony Burton. In a couple of sentences, what is the main advantage of fusion over fission?
Yeah, that's fair. The major one, or the number one which people talk about, is in my background's fission as well. So is essentially for fusion, it's very difficult and or near impossible to have a chain reaction. So the idea of chain reactions in fusion is obviously you split uranium and then it continues splitting under its own environment, and then you have to control the environment to stop the chain reaction or moderate it or control it to such a level that is now what we call commercial fission. In fusion, you just don't have that. There is no case of meltdown from, at least from the fuel itself or from the fusion reaction or from the nuclear section of it. It's hard enough trying to heat up fusion to get fusion to work. You do have to maintain the reaction by either its own self-heating, and also there's heating systems which I haven't mentioned about, which actually fire. But in this case, it's commercial. Let's say it's magnet confinement. There's ways you have to keep heating the plasma through a solenoid or through firing neutral particles into it. So there's no meltdown. If the machine, if the power turns out on a fusion reactor, the fusion dies. That's a problem for a commercial standpoint, really, as there is no way to keep it going on its own. That makes sense.
Are there any significant environmental or safety risk for a fusion reactor? There's a question there from Natalia Edwards.
So it's a good question. It's what we specialize in as an organization as well. Safety into fusion it's more seen to as more of a chemical, radiological safety aspect. Again, it depends on the technology, depends on the design, but if you take just magnet confinement using a tritium fuel cycle, tritium is radioactive, so it's radioactive gas or radioactive hydrogen. So there's obviously implications on radiological protection surrounding that. The quantity of it is also can be a challenge for power stations, but it's not, I think, it's nothing new. That makes sense. You know, it's a well-known managed safety perspective. Other things that fusion does produce is it does produce radioactive waste, but it's just on a different magnitude compared to fission. Most of the waste decays in hundreds of years to 1,000 rather than 10,000 to 100,000, depending if it's on the fuel cycle. So there's different levels of, you know, it's a different form of waste. A lot of it is structural waste, so it's structural steels, it's structural components, if that makes sense. That sort of aspect. So the safety profile is different. It's more akin to large-scale chemical plants with handling radioactive material, if that makes sense, rather than a sort of nuclear safety, traditional nuclear safety of surrounding criticality and surrounding maintaining the control of fission, for example.
Is it resistant to flooding? After we had the issue in Japan with the flooded fission reactor, and Mark Watson points out that the new STEP plant is quite close to the River Trent.
Yeah. I can't comment on the design of STEP, but in terms of flooding itself, you don't need to have systems online to maintain the shutdown of fusion, for example. So it's different to Fukushima, where obviously you have backup diesel generators, which supported the recirculation of the cooling water. You generally don't need to do that, at least based on current designs. I would also caveat all this in saying, as people who work on safety, safety is obviously driven by operational experience as well, knowing how things operate. As you can probably tell, there's been no operations of a power generating fusion power station. So there's still a bit of learning to do, but based on all the knowledge and experience we have now across all industries, we don't see any major showstoppers yet. But that doesn't give you, I would say, it doesn't give you thought to be complacent on it either. But yeah, I can't comment on step design specifically. I do know there's a River Trent there. You do need a river to cool the if you're making power. Same with any other power station. You cool obviously the steam cycle.
Thanks. A couple of specific questions before we go on to some more global ones. Who are the organisations competing to be the engineering, construction and fusion partners? That's a question from Chris David. And from John Wood, we have, what happened to IFMIF, who are testing fusion materials?
Yep. So, yeah, I can comment on both. For the first one, who is competing on engineering partner and construction partner, I'm going to avoid myself of saying anything because it's commercially sensitive. I'm not going to say on on a webinar. But there are organisations out there. I think the other way to answer that one without being actually answering like a politician is whenever there is a next public meeting about that partnership, which UKAEA will host. If you attend that meeting, you'll find out who's probably interested.
Okay.
Yeah, that's a very non-answer. Sorry. If that was the question. So I put International Fusion Materials Irradiation Facility. I think that's what it stands for. There's actually two. There's IFMIF and there's IFMIF Donez. IFMIF has been built in Japan. It is one of the technical challenges in fusion is, I didn't really allude to it, is when you fuse deuterium tritium, it gives off a neutron. That neutron has a particular energy spectrum, which is unachievable in fission right now, so we can't actually probe it. So it gives us these neutrons which hit all the walls, and the company that I run focuses on that sort of technical challenge. We are in a position right now where we don't have access to the environment to test materials, which will be seen in the power station. We can make analogous to fission. We use fission reactors for this and use other source of radiation to do it. So IFMIF is designed specifically to generate a fusion neutron source at the intensity levels required to sort of probe that power station facility. It's currently being built in Japan as part of the ITER consortium, and is to support ITER and support the demo programs for the future. I did mention IFMIF Donez, which is kind of a subset of that. It's a shorter time scale construction that's been built in Granada, Spain. Again, part of the ITER sort of Eurofusion program, which is the European effort on fusion. Again, fusion neutrons environment to really test and develop materials, which we do, and we're part of that sort of cohort of people. Yeah.
We have a comment rather than question from Sue Pearson, who says that she worked on ITER, the preliminary design of the buildings in 2010, and one of the things they were concerned about risks was earthquakes. So, and then I have also a number of sort of broader questions. So from Ian Harris, who congratulates you on the talk, Tom. Ian's comment is, I am over 60. I always thought Ian is younger than that. Spent my entire adult life thinking that fusion energy is 30 years away. So where do you think is a realistic time scale? Clive Bullen asks, what kind of proportion of global energy could we get from fusion? And I guess ultimately, and we have a couple of questions from Rupert Stubbs. Rupert has concerns that America will monopolize all the talent as post John Kerry's unveiling of the plan. And in the light of that, could you tell us anything that you're aware of that's going on in China?
Okay. All right. The first question, if I remember these in order.
The last bunch of questions, I think.
30 years away, is that right? Yeah. Fusion's 30 years away. I don't actually have the graph. I wish I had the graph which defines where 30 years come from. It actually comes from somewhere. It comes from a US. I'll answer the question of why 30 years away arose and why I never met that statement. And then I'll answer it in a way which doesn't actually answer the question, but gives you some thought. So in 1976, there was a Department of Energy, the name before Department of Energy, had a report out at the time of current fusion funding in 1976. This was just before the oil crisis, by the way. They had a scenario basically, which had different scenarios of costing, of funding to fusion to get to power station, essentially. There was one which says fusion, aka never, and there was a funding line that just basically plateaued out for the next 30 years or 40 years, just went on, right? So basically, you never achieve power station for fusion. There was the one which was the modest funding program and had some dollars per year of funding, and it reached to 2005 when you get fusion power, and that's actually 30 years from 1976 to 2005, 2006. And then there's a plot on that same curve, retrospectively in mid-2000s, someone plotted on the actual funding allocated to fusion post that report, and it basically drops off to near, hundreds of millions of dollars a year, which is insignificant to the billions that was being proposed in 1976, billions. The point of the story really is it was never going to achieve 30 years from that report because the funding never came with it. Also, I would also state that funding doesn't necessarily mean success. It doesn't translate to success. It just translates to the potential of being successful. So obviously there's some technical milestones which need to be overcome as well. So the answer is that's where the 30 years come from. But to answer your question, is it still 30 years away? I would say the realistic answer is it will be when we want fusion as a globe. I think when the governments, whoever it may be, or whether it's when we actually want fusion as a commercial source, I think that'll be more of the approach for that, which is not again a non-answer. The other ones, global energy proportions for fusion. I right, I would say it's quite uncertain from my perspective. If you again base it on a fission-based model, you know, you're talking like 20%, but it's very country dependent, country specific as well.
Good. If you could make
yeah,
on China, because we're going to have to finish there in just a minute or so.
Yes, China do have 2 private fusion organizations from what I'm aware of. From my personal experience, I've had no interaction, and information from those organizations is quite difficult to get hold of in the public domain. Other than that, we being the fusion community in the West, have little insight into the Chinese program. I would say the Chinese government program, which is somewhat public to an extent, it's been published in academic journals, has a program to deliver a power station, you know, in the coming decades to come. They are building a lot of infrastructure, a lot of equipment there now. So we'll sit and wait. You know, they are definitely heavily thinking about fusion as a potential energy source for the future, and are doing generally their own thing on it as well. Whereas I say, you know, with the UK and US, we're very much sort of collaborative, which kind of hits on the other question about will the US just mop up all the talent? I would say not necessarily, because the UK right now is currently leading in fusion development with the UK Atomic Energy Authority in Culham. I mean, Oxfordshire is probably the largest concentration of people who are upskilled in fusion in the world, of highest concentration. I don't see that changing anytime soon.
That's very good news to end on. I've sent a few responses to some of the other questions.
Yep.
Tom, I'd really like to thank you very, very much for giving your time. That was fascinating. And for those of us who found that interesting, I'd like to say that this is one of many of these lectures, these Knowledge Mile lectures. Next Tuesday, we have one on the ending the destruction of our undersea cultural heritage. Next Thursday, the opportunity in digital manufacturing. And on next Tuesday, the 12th, is today's financial literacy education fit for purpose, a subject after my own heart. So thank you very much indeed. And I think we will finish the webinar there with, as I say, further thanks to Tom and to everyone.
Thank you.